Section 4.7, Variable Coefficient Equations. In this section, we consider second-order linear equations of the form a2 of t y double prime of t plus a1 of t y prime of t plus a0 of t y of t equals 0. Notice that this is just one of our standard forms for a second-order linear homogeneous equation, but this time we have non-constant coefficients. As you may recall, another appropriate standard form is to divide through by the leading coefficient, which we know cannot be 0, and rewrite this with a leading coefficient of 1, where we just divide through by a2, and so we get a leading coefficient of 1. a1 over a2 becomes a new function p of t. a0 over a2 becomes a new function q of t equals 0. And we'll call this equation 1. This will be our reference equation for this section. So suppose we have some solution y1 of equation 1. The question here is, can we manufacture a second linearly independent solution, y2? And the key here is going to be reminiscent of variation of parameters, although this is a very different setting, but it's going to be reminiscent of that in the sense that we're going to look for a new solution that has the form of an old solution times an unknown function. You may remember with variation of parameters, we had a fundamental solution set, y1 and y2, of the homogeneous problem. And so to look for a particular solution of the non-homogeneous problem, we looked for a yp of the form v1y1 plus v2y2. This has the same theme, if you will, except here we have fewer moving parts. We just have y2 equals some yet to be determined v of t times y1 of t, where here y1 is known and v of t is to be determined. So here's what we'll do. If y2 is going to be a solution, then we know when we substitute it back into our differential equation, 1, then we must get a logically true statement. So in preparation for that, let's calculate some derivatives. So we'll suppress the dependence on t here in the notation, but remember all of these are functions of t. So we'll take the derivative with respect to t of y2. By the product rule, we get v prime times y1 plus v times y1 prime. If we take the derivative again, we have a product rule here to get these two terms. We have a product rule here to get these two terms. And notice after we consolidate, we get what's shown here in the red. Now, when we substitute back into the differential equation, if y2 is going to be a solution, then y2 double prime plus p times y2 prime plus q times y2 has to be 0. So here we'll just substitute in what y2 double prime is here. We'll substitute in what p times y2 prime is here. And we'll substitute what q times y2 is here. So here's y double prime plus p times y2 prime plus q times y2. Now we're going to regroup, and I've tried to color code things here so you could track what's happening. So we'll just group things according to, why don't we look in first, in green here, we've color-coded everything that has a common factor of just a v in it. Just a v in it. So let's group these terms together and factor out that common factor of v. Secondly, in red, this is the only term that has a v double prime in it, so let's have that by itself. And then we have two of these terms that have a v prime in them. Let's group them together and factor out the v prime. So now, if you look at this form, the expression in parentheses, y1 double prime plus py1 prime plus qy1, that's not a random configuration there. That is, we know that y1 is a solution to our homogeneous problem, equation 1, so when we substitute y1 in, we must get a 0. That means the green term vanishes. And now we're just left with the red plus the yellow equals 0. So now let's look at that for a moment. Let's just rewrite this here. And now if you stare at this, y1 is a known function. P is a known function. If y1 is known, then y1 prime is known. And the only unknown in this entire equation is v. And in fact, this is a differential equation in the unknown v. It's a second-order differential equation in the unknown v. The key here is that y1 and p are known functions. And because this has a v double prime and this has just a v single prime, notice this has a very special structure. We don't have just a regular v term. We're going to use a stunt called reduction of order, and it works when you have terms that are present like this, a v double prime and a v prime in the absence of a v. And now it'll feel sort of like a u substitution, and you'll see why we call it reduction of order. We're just going to introduce a new variable called u. We'll let u be v prime, If u is v prime, then u prime is v double prime. And now if we just substitute here, everywhere we see a v prime, we'll put a u. Everywhere we see a v double prime, we'll put a u prime. And notice it translates this equation in black here, which is a second order equation in the unknown v. It translates this into the red equation, which is a first order equation in the unknown u. Still a differential equation, it's not an algebraic equation, but at least we've reduced the order of the equation, and this is why we call this technique the reduction of order technique. If you look at this a little bit more closely, the red equation, if you divide through by y1, and remember that y1 is known, so y1 prime is known, and p is known, that means this entire coefficient function is known. If you look at this equation, this is a first order equation in the unknown u. In fact, it's a separable equation, but it's also a first order linear equation. So we can use either of our chapter 2 techniques to solve this equation for the unknown u. Now here in the notes, just for the sake of specificity, I will solve the equation as a separable equation, but you could also use an integrating factor and solve it just as well. So if we solve this as a separable equation, we'll just rewrite the u prime as a du dt. We'll throw this term to the other side. And if you separate this multiplicatively, you get du over u equals this stuff. And remember, all of this is known. So now we anti-differentiate this side, we anti-differentiate this side. And when we anti-differentiate, the left-hand side is pretty straightforward. This is just the ln of the absolute value of u. We have to work a little bit more to calculate this integral on the right. And if you look at this, if we algebraically prepare this, if we just divide each of these by y1, so we separate this, then we get two integrals here. And now this integral, the p function just is what it is, so this antiderivative just is what it is. The question is what to do here. Well, now we can just do a little baby u substitution. We've already used the letter u, so let me use another letter. How about w is y1? Then dw would be y1 prime of t dt. And if we make this substitution, this integral here translates into this integral. We can anti-differentiate this as the natural log of the absolute value of w. Here we're just leaving this alone. And now if we translate back, remember w was y1, so this is an ln of absolute y1. And now using a little property of logs that a ln of b is ln of a to the b, or b to the a, then we have this as ln of absolute y1 to the minus 2 minus the antiderivative of p dt. So now let's just copy and paste this, which is just the antiderivative of this. Let's put this in here. And let's keep our eye on the prize. We want to know what u is. So we want to unravel this absolute value of u from inside this natural log. So we'll apply a base e exponential to both sides. Now notice all of this is up in the exponent of the base e exponential. E to the ln of the absolute value of u is the absolute value of u. Here, e to the a minus b is the same as e to the a times e to the minus b. And now if we drop the absolute values, we pick up a plus or minus sign here. If we simplify this, we just get absolute y1 to the minus 2, and this just is what it is. And here with the plus or minus, I'm just looking for any u that solves the equation. I don't have to find every single u, so I'm just taking the positive one. And now if we just rewrite this, this is the absolute of a y1 to the minus 2, which is the same as a y1 squared in the denominator. And notice we have solved our equation for u. P is a known function and y1 is a known function, so now we have our hands on u. But remember, we were wanting v, not u. So u was just v prime. So v prime is equal to this. And now we will get what we wanted, because if we want to find v, we just need to anti-differentiate both sides of this. And notice what we've found here. This is a formula that we need to remember. This is the recipe for the function v that we need to multiply. Remember what we were trying to do. We had a known solution to equation 1. We were trying to manufacture a second linearly independent solution to equation 1. And so we were looking for one that we could just take our old solution and multiply it by some magic function. And we just deduced what the magic function is. Call it star. Okay, so now how might we apply this? Well, think back to when we were doing case 2 of the characteristic equation for the constant coefficient homogeneous situation. So we had ay double prime plus by prime plus cy equals 0, and we would write down the characteristic equation. we would find the roots of the characteristic equation, and then we broke this down into either a case 1, a case 2, or a case 3. Let's focus on case 2 because I owe you an explanation for something we did back in the notes in case 2. If you remember, case 2 was when the discriminant of this quadratic was 0. That means that we got a double root, and the root is minus b over 2a. Back when we were explaining this, we said, well, if we have a double root, then we know one solution to our equation is e to the RT, where r is our root. And then the question was, how do we generate our second linearly independent solution? Because our theory said we needed two linearly independent solutions to build the general solution, YH. And now, if you remember what we said back then, is we just declared that what you need to do is take your old solution, e to the RT, and we just declared that in case 2, in order to get a second linearly independent solution, you needed to take your old solution, e to the RT, and multiply it by a t. Now you'll see where that came from. So let's act like we didn't know that that was the answer, and let's just play along and say, hey, I've got one solution. I've got one solution to my equation. I want to find a second linearly independent solution. I want to build a second linearly independent solution to this equation. Well, the method of reduction of order just said you should look for a solution that looks like y2 equals v times y1. And we had the boxed in star formula recipe for what v is. We just need to pull the ingredients from our original equation. We need to pull the ingredients for p and q. Now you have to keep in mind that in order to use this, you must have your equation in the form, not of the way it stands right now. We must have our differential equation in the form where the leading coefficient of 1. So before we just start grabbing the p and the q, we need to take our differential equation, make sure it gets a leading coefficient of 1, divide everything through by a, and now this is our p, and this is our q. That's a very easy mistake to make, so be aware. So now we know that our v has this recipe, where this is my p, and this is my q, but only p is in this formula. And we had our v1, our y1, I'm sorry, right here. So now we'll just substitute in that p is b over a. We had that our y1 was e to the RT, where r is a known quantity. And now we'll simplify this. If you anti-differentiate b over a with respect to t, you get b over a t. And so this becomes an e to the minus b over a times t. This is just an e to the RT quantity squared. Well, r was minus b over 2a, so this is an e to the minus b over 2a times t, quantity squared. And if you simplify this, then when we simplify this, we get this. And notice, after the 2's cancel, this is an e to the minus b over a times t over an e to the minus b over a times t. Those cancel. We get the antiderivative of 1 with respect to t, which is just t. And that was the magical multiplier from case 2 back when we were studying the characteristic equation. So I just declared to you that, hey, we need to take our e to the RT, and to get the second linearly independent solution, you just take your first solution, you multiply it by t, and now you see where that came from. So our second solution is v times y1, which in this case is t e to the RT. And the theory guarantees that it will be linearly independent. We haven't proven that here, but back when we were doing the characteristic equation material, we actually proved, we computed the Wronskian of our e to the RT and our t e to the RT and showed that it was not 0. So in fact, it is linearly independent. We just don't have it here because we've already done it. Let's take a look at an example that's a little bit different than our constant coefficient equation. We want to show you that the method of reduction of order is more broad than that. So suppose you have the equation t squared y double prime plus 6t y prime plus 6y equals 0 for t that's positive. Well, if we rewrite it and let's suppose that we were told that one solution to this equation is t to the minus 2. Now, you would have to be given that. So let's suppose that you've been given one solution. And the question is, can we find a second linearly independent solution, y2? Well, we're going to use reduction of order. This is tailor-made for this. In order to do that, we need to get a leading coefficient of 1. So we will divide through by t squared. And after you simplify, you get this. Notice that our p here is 6 over t, or you could write it as 6 times t to the minus 1. We're going to look for a y2 that has the form v times y1. We know the recipe for our v is this. We're just going to compute these pieces. So I'll go off to the side. I'll grab this numerator. We'll go off to the side and compute this integral. So we have e to the minus integral of my p of t dt. P is 6t to the minus 1. So when we anti-differentiate this, this is just if you pull out the 6 and you anti-differentiate 1 over t, you get ln of absolute value of t. But they told us in the problem that t was positive, so the absolute value of t is the same as t. Now we'll use our little property of logs. This is algebra, not calculus. We'll use our little property of logs to rewrite this as this. And the reason that that's beneficial is now the e and the ln can cancel each other, and you're just left with a t to the minus 6. So notice that this is just the numerator in this longer formula for v. So we will replace the yellow with this t to the minus 6 highlighted in yellow. The denominator, remember they told us that one solution y1 was t to the minus 2. We do need to square it. When this simplifies, we get a t to the minus 6 divided by a t to the minus 4, which is the same as multiplying by a t to the positive 4. So we get a t to the minus 2. This is a straightforward power rule to anti-differentiate. We get t to the minus 1 over minus 1. We don't need the plus c because we're just trying to find any v that works. We don't have to find every v that works. And so this gives us a minus t to the minus 1. Now be careful, this isn't our final answer. Our final, what we're looking for is a second linearly independent solution to our differential equation. And so remember, this is just the magic multiplier. So we're going to go back to y2 is v times y1. We knew our y1. We just calculated our v, and then we'll simplify this to get minus t to the minus 3, and that is our second linearly independent solution that we found by using a reduction of order technique. Notice you don't actually see the reduction of order happen here. It's behind the scenes, and it's built into the argument that transpired when we were calculating v. So just a word of wisdom here on the homework. In the online homework, MyLab only has one of these in MyLab for you to practice for using the method of reduction of order. Not every homework problem in the textbook is programmed into MyLab. So I've assigned number 43 from the textbook number 43. I've assigned it in MyLab. But I would definitely recommend practicing this more than one time. And if you actually look at the ebook, not what's in MyLab, but actually look at the ebook, a PDF version of the textbook, they have 41, 42, 43, and 44 are all reduction of order, where they give you a differential equation. They give you, it's not, and it might have non-constant coefficients. As a matter of fact, I think they all do. And they give you one solution, and they ask you to build the second linearly independent solution. So it's exactly like this example, and I urge you to try that so that you get more than just one time to practice it. Okay, so in keeping with the title of this section was variable coefficient equation, so what we're doing is we're exploring both some theory and some solution techniques for very particular variable coefficient equations. So we're not trying to solve them all. That's a greater task that we'll look at more in Chapter 8. But for right now, we're just trying to do what we can. And one thing was we wanted to establish the method of reduction of order, put that in our toolbox, be able to build a second linearly independent solution in the general situation when we only have one solution, because that will help us flesh out our general solution to the homogeneous problem. And then we want to turn our attention to a very special category of variable coefficient equations. And they are second order linear homogeneous equations, but they have to have a very particular look in their coefficients. They have to look like ax squared y double prime of x plus bx y prime of x plus c y of x equals 0, where the leading coefficient cannot be 0, but it's okay for b and or c to be 0. These are called Cauchy-Euler equations, and they occur in a variety of problems. In particular, they occur in some mathematical physics problems that you will see if you continue on into Math 3326. Partial differential equations, these are a popular category of equations. And it turns out that even though variable coefficient equations are in general very complicated to solve, that this special class of equations are something that we can solve quite handily. So people that came before us, they said, well, why don't we look for solutions of a particular form? And if you think about it, this looks like a constant times my function plus a constant times x times the first derivative of my function plus a constant times x squared times the second derivative of my function. And I think the people that came before us said, well, if I guess a power function, when I take the first derivative, I know the power is going to be reduced by 1. And when I take the second derivative, I know the power is going to be reduced by 1 again, so it's going to have been reduced by 2. And if the first derivative is reduced by 1 power of x, but I'm multiplying by 1 power of x, that means that these together will have the same power that this has. And similarly, since this power was knocked down by 2, but I'm multiplying by an x squared, that means this will also have the same power as this. So it's as if we have a fighting chance to find a solution of this form. So why don't we see if there's a p that will make this a solution? So in keeping with what we've done the entire course, we're just going to say, well, if this is a solution, we'll pre-compute its first and second derivatives. We'll plug back in y, y prime, y double prime in here. We will simplify, and if you stare at this, after we plug these in, we can factor out the common factor of x to the p. Remember, p is yet to be determined. When we do that, we get an AP times p minus 1 plus a BP plus a C, so that what's in brackets. If we expand this out in collect terms, this becomes an AP squared plus B minus A quantity times P plus C. So this is a factored form of this polynomial, this quadratic equation in P. So either x to the P is equal to 0, or this quadratic equation is equal to 0. And notice that if x to the p were equal to 0, then that says x is equal to 0. But if you stare at the form of the equation, x can't be 0, because if x were 0, this is not even a differential equation. This term would vanish, this term would vanish, because of the coefficient x that's present. So we'll rule that out, and we'll say, well, it must be then that this must equal 0. We'll call that star. And this is called the characteristic equation for the Cauchy-Euler equation, or the Cauchy-Euler characteristic equation. Notice I purposefully used a different letter here. I used P. Really, it came from looking for a power function that was a solution. But it's convenient that we did not use the same letter R that we used before, because notice this does not have exactly the same form. Before, we had AR squared plus BR plus C equals 0 for our characteristic equation. But this time we have AP squared plus B minus A times P plus C. So you have to remember this little shift that occurs when you're looking at a Cauchy-Euler equation. Okay? So now we have 3 cases. This should sound like a familiar story that we've seen before. We have 3 cases for the roots of our Cauchy-Euler characteristic equation. Case 1 is we have 2 distinct real roots, P1 and P2. If you do that, then you get one solution that's x to the P1. You get another solution that's x to the P2. And the P1 and the P2 powers can't be the same. If you were to check the Wronskian on these two, it's not 0. So that means these are not only solutions, they are linearly independent solutions. So that means we can build the general solution to the Cauchy-Euler equation in the case 1 situation as C1x to the P1 plus C2x to the P2. Okay? Now, case 2 is what happens if we have one repeated real root, we'll just call it P, for the Cauchy-Euler characteristic equation. If we do, then we have y1 equals x to the p, but remember, our theory says in order to build the general solution to the homogeneous problem, we must have a second linearly independent solution. So now we need to manufacture a second linearly independent solution, and this is why we learned reduction of order in this section. What would we do with this equation if we knew one solution? So remember, A, B, and C are known. We know one solution, and we're trying to manufacture a second linearly independent solution. Well, what we would do is we would let y2 equal some yet to be determined v times y1. We know our y1. We would build our v using reduction of order technique, using the formula for v that we saw in the previous examples. Now, if you do that, I'm not showing it here, but if you do that, you will get that your v is the natural log of x. You just have to go through and do the calculation. And when you do, you get this. So the magic multiplier in case 2 for the Cauchy-Euler equation isn't just x or t, it's ln of x. And that's because that's just the way the calculus and the algebra shake out in the the reduction of order argument in this particular differential equation. So that means one solution is x to the p, the other solution is ln of x times x to the p. So that means our general solution can be written as c1 x to the p plus c2 ln of x times x to the p when you're in case 2 for the Cauchy-Euler equation. Now for case 3, suppose you have a complex conjugate pair of roots, so p is alpha plus or minus beta I. Well, then one solution will be x. Remember, we were looking for solutions of the form x to the p. So if this is our p, let's just grab the positive one first. One solution will be x to the alpha plus beta I. We can split that as x to the alpha times x to the beta I. Now in the past, we used the Euler-Domar formula to simplify our complex exponential. Here we have to work a little bit more. So here we'll just say, well, x, look at the red. X is another name for x is e to the ln of x. And so if x in red is equal to e to the ln of x, I can raise both sides to the p power in blue. And so that means x to the p is the same as e to the ln of x, the entire thing to the p. And now e to the ln of x raised to the p is just e to the p ln of x from algebra. So that means if you have an x to the any power, it's just e to your power times the ln of x. So here I have an x to the beta I, so it's e to the beta I times my ln of x. So I'm just using this formula where p is beta I. And now I can use Euler-Domar on this because Euler-Domar told me how to do e to the I theta, where this is my theta. So I'll leave this alone. E to the I theta is just cosine theta plus I sine theta. My theta is beta times ln of x, just writing it over here. And so now if we distribute the x to the alpha, and then remember our theorem that said if you have a complex solution to a linear homogeneous differential equation, then you can extract the real part and the imaginary part, and those creatures will themselves be solutions to your real solutions to your differential equation. So if we extract this real part, we extract this imaginary part, those two are solutions. In fact, you have to check me on this, they are linearly independent if you just calculate their Wronskian. So that means one solution to our equation in this case is x to the alpha cosine beta ln of x. Another solution is x to the alpha sine beta ln of x, and they are linearly independent. Therefore, our general solution, YH, can be written as a linear combination of these as C1 x to the alpha cosine beta ln of x plus C2 x to the alpha sine beta ln of x. Let's look at some examples for these. So find the general solution of this differential equation, here where x is positive. Now the first thing you have to be able to do is spot this as a Cauchy-Euler equation. Notice it has the pattern ax squared y double prime plus bxy prime plus c times y equals 0. It does have that pattern. Our a here is 1, our b here is 2, our c here is -6. You also have to remember that the Cauchy-Euler characteristic equation isn't ap squared plus bp plus c like we're used to doing. It's ap squared plus b minus a times p plus c equals 0. Remember that shift. So when we substitute in our a, our b, and our c, then we get p squared plus p minus 6 equals 0, which factors like this. So our roots are this. These are distinct real roots, so we're in case 1. So we get our homogeneous solution is c1x to our first root plus c2x to our second root. And this is what the general solution to this Cauchy-Euler equation is. Another example, suppose we have this Cauchy-Euler equation, x squared y double prime plus 9xy prime plus 17y equals 0. Again, our a is 1, our b is 9, our c is 17. We write down the Cauchy-Euler characteristic equation, remembering the shift. When the dust settles, we get this. That's not going to factor over the reals, so we use the quadratic formula. And when we do that, we get that the roots are -4 plus or minus I. So our alpha here is -4, our beta here is 1. We're in case 3. And so our general solution is going to be C1e to the alpha cosine beta ln of x plus C2x to the alpha sine beta ln of x. And that's our general solution. Okay, third example. If we have this Cauchy-Euler equation, we can spot because it matches the pattern ax squared y double prime plus bxy prime plus cy equals 0. Our a is 1, our b is 7, our c is 9. This is our Cauchy-Euler characteristic equation, remembering the shift. This reduces to this, which factors like this. So our root, we have one root, we're in case 2. Our root is p equals minus 3, and it's a double root. So our general solution is yh is c1 x to our p plus c2, here's the magic multiplier in the Cauchy-Euler situation, ln of x times x to our p. So we see that we've been able to kind of give an overview. What we've done in this section is we've used the method of reduction of order to generate a formula that will always enable us to manufacture, if we know a single solution to a variable second order linear homogeneous equation with perhaps variable coefficients, then we can always generate a second solution, y2, that looks like v times y1. We have a recipe for v. That led us to it answered a question from back in the constant coefficient situation. What was the magic multiplier in case 2? We found out that it was just t. And then when we confronted this new category of variable coefficient equations, the Cauchy-Euler equations, we were able to do an analogous characteristic equation type method to look for power functions as solutions. And again, the method of reduction of order came to the rescue in case 2 and told us what the magic multiplier was. It told us that in the Cauchy-Euler situation, the magic multiplier for case 2 is ln of x.